There's a revolutionary idea in deep learning that turned sequence processing on its head and then leapt beyond language to transform computer vision.
We've touched on transformers before, like in #TCM183004, where we saw how they excel in understanding context. But what was the big shift this paper introduced?
Exactly. Before this paper, the state-of-the-art for sequence tasks often relied on complex recurrent or convolutional neural networks.
But the authors proposed something radical. They asked, what if you could do away with all that complexity?
And their answer was attention?
Precisely. The paper introduces a new architecture based solely on attention mechanisms.
Wait, solely on attention? So no more LSTMs or CNNs in the core model?
That's right. They explicitly state it's dispensing with recurrence and convolutions entirely. This was a huge departure from dominant approaches.
But if you're processing everything in parallel and not sequentially like an RNN, how does the model know the order of words? Like dog bites man versus man bites dog.
That's a crucial observation, Maya. Without recurrence or convolutions, the natural order of the input sequence is indeed lost. This means the transformer, on its own, is inherently permutation invariant. We'll see how it addresses that fundamental challenge in the mechanism section.
This attention-only design wasn't just elegant, it was incredibly practical. It made models more parallelizable during training.
Parallelizable means faster training, right? Like running parts of the calculation simultaneously?
And the speed gains translated into better results. They achieved superior in quality results on machine translation, beating previous state-of-the-art.
So, a simpler model, faster training, and better performance? That sounds like a dream.
They backed it up with numbers. For English to German, their model achieved 28.4 blue, which is a score from 0 to 100, measuring how closely a machine translation matches human reference translations, significantly improving over prior bests.
That's a pretty convincing jump for a benchmark like blue.
And they immediately showed its general applicability, stating it generalizes well to other tasks like English constituency parsing.
So the core idea isn't just about translation, it's a new way to process sequences in general?
Exactly. The big question became, if attention is all you need for language, what is attention intuitively? Let's build that picture piece by piece. To really understand what attention is all you need means, we need to peel back the layers. This illustrated guide helps visualize it.
So, how does this attention-only model actually work at a high level?
At a high level, it still has an encoding component and a decoding component, much like earlier sequence-to-sequence models.
Okay, so the overall structure isn't completely alien. It takes an input, processes it, and generates an output.
And if we zoom into one of these encoder blocks, we'd see it's typically made of two main sublayers, a self-attention layer and a feed-forward neural network block.
So attention, then a standard neural network block?
Yes, and around each of these sublayers, there's also a residual connection followed by layer normalization to aid stable training and information flow. This entire block structure repeats 6 times for the full encoder stack.
6 layers, each with attention, feed-forward, and normalization. That's quite a bit of processing.
Let's use the classic example to understand self-attention. The animal didn't cross the street because it was too tired. What does it in this sentence refer to?
The animal, obviously. A human knows that.
Self-attention gives the model that human-like ability to link words, While it gives the model human-like ability to link words, it's a statistical association, not genuine semantic understanding like a human's, which can grasp irony or deeper context. As the model processes it, self-attention allows it to associate it with animal.
So it's letting the model look around the sentence to understand what a word really means in context?
Yes, precisely. It allows it to look at other positions in the input sequence for clues to better encode the current word.
This sounds a bit like an RNN's hidden state, carrying information forward.
It's a good analogy for the purpose, Maya, but not the mechanism. RNNs process sequentially. Self-attention does this by baking the understanding of other relevant words into the one we're currently processing in a single parallel step.
This baking happens in a way that allows each word's processing to happen in parallel, unlike the sequential nature of RNNs. That's why the various paths can be executed in parallel in the feed-forward layers as well.
Ah, so this is how it achieves the more parallelizable benefit we saw in the first paper?
To achieve this contextual blending, self-attention uses three special projections of each word: a query vector, a key vector, and a value vector.
Query, key, value. That sounds like a database lookup system.
It absolutely does, and that intuition is powerful. But the lookup here is more like a learned interpolation. Unlike a precise database lookup where you get an exact match, here the lookup is fuzzy and learned, resulting in a weighted blend rather than a single distinct piece of information. Let's see how they interact in detail.
We've got our query vector, key vector, and value vector for each word. Remember, these are learned projections of the word embeddings.
And the QKV vectors are what makes self-attention work?
First, for any given query word, say it, we calculate a score against every other word's key vector. This is done with a dot product.
So query and key determine how relevant other words are to the current word?
Exactly. Think of it like that. Though relevance here is purely mathematical, how strongly their vector representations align via dot product, not an intuitive human judgment of importance. If we're processing the self-attention for the word in position number 1, the first score would be the dot product of Q1 and K1. The second score would be the dot product of Q1 and K2.
So a high dot product means the query word pays more attention to that keyword.
Next, we divide these scores by the square root of the key dimension for stability, then pass the result through a softmax operation.
Softmax. That turns the scores into probabilities that sum to 1, right?
Yes, these softmax scores are the actual attention weights. They determine how much each word will be expressed at this position.
So for it, the softmax score for animal would be very high and low for street?
That's the goal. Finally, we multiply each word's value vector by its corresponding softmax score and sum up the weighted value vectors.
And this sum becomes the new context-aware representation for our query word?
Precisely. The intuition is to keep intact the values of the words we want to focus on and drown out irrelevant words. The analogy of drowning out is strong, but more accurately, we're giving highly relevant words much stronger weight, effectively diminishing the influence of less relevant ones rather than completely eliminating them.
So the query and key vectors act like a sophisticated search and relevance engine, and the value vectors are the actual information being blended.
Okay, I get how attention blends information, but you mentioned earlier that processing words in parallel loses their order.
how does the transformer know the difference between, say, dog bites man and man bites dog?
That's a critical point, and it's where positional encoding becomes essential. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence. So before the word embeddings even enter the transformer, we add a special vector to each embedding based on its position.
So it's not just dog, it's dog at position 1?
Precisely. These positional encodings are often fixed patterns like sine and cosine functions. They ensure that even though all words are processed simultaneously, the transformer still understands their relative and absolute placement in the sentence. The positions are added to the word embedding vectors.
What we've just detailed is essentially a single attention head, but the transformer takes this a step further with multi-head attention.
Multi-head? So multiple sets of query, key, and value vectors processed in parallel?
Precisely. Multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. Imagine each head specializes in a different kind of relationship. One might look for syntactic links, another for semantic connections, and another for dependencies across longer distances.
So it's like combining the insights from several specialized experts looking at the same input simultaneously, giving a much richer contextual understanding for each word.
Exactly. The outputs from these multiple heads are then concatenated and linearly transformed, giving us a more comprehensive and robust contextual representation for each word.
This entire process, query key value attention with positional encodings and multi-head processing, is what we introduced in TCM 183004. This guide just showed us the inner workings.
And this is what replaced all the recurrence and convolution in the original transformer.
This mechanism is incredibly flexible. Any data that can be represented as a sequence of vectors and injected with positional information can benefit from this dynamic contextual blending.
So it's not just for words anymore. This general attention idea is the key, adaptable to different data types.
Exactly. This generalized power is what made researchers wonder, could this attention-only model, so effective with language, also work for images?
Once the transformer proved its might in NLP, the question for researchers was, could this attention-only paradigm apply to other domains, specifically computer vision?
Images are so different from text. Words have a natural sequence, but pixels are a grid. How would attention handle that without convolutions?
That's precisely the challenge. The breakthrough came from a deceptively simple idea, formalized by the Vision Transformer, or VIT, which treats parts of an image like words. First, it splits an image into fixed-size patches.
Patches, like little squares across the image?
Exactly. For example, a 224 by 224 pixel image might be divided into 16 by 16 pixel patches. Each of these squares is then linearly embedded into a sequence of flattened 2D patches, essentially converting each patch into a vector.
So each 16 by 16 patch becomes a single token or word in our sequence?
That's the conceptual leap. These flattened patch vectors are then treated exactly like the word embeddings in the original transformer. Crucially, they also add positional embeddings to these image patches, so the model retains information about where each patch originated in the original image grid. These image patches are fed into a transformer encoder.
So you transform the image into a sequence of patch embeddings, add positional information, and then feed that into a standard transformer encoder, just like with text.
Precisely. The transformer then processes these image patches, attending to relationships between different parts of the image across the entire input without any initial convolutional layers.
This approach is powerful, but it's important to note a key difference from CNNs. Traditional CNNs have strong inductive biases like translation equivariance and locality. They're hardwired to understand local spatial relationships.
So CNNs are good at recognizing features like edges and corners automatically because those patterns are local?
Exactly. Transformers, by contrast, are more general purpose. They initially lack some of the inductive biases inherent to CNNs. This means they need to learn these local relationships from scratch, which requires a lot of data. The paper states VIT does not generalize as well when trained on insufficient amounts of data.
So while they offer global context from the start, they might struggle with smaller datasets where CNNs excel.
That's right. But when trained on massive datasets like JFT300M, a proprietary dataset of 300 million images, they achieve state-of-the-art results, often surpassing CNNs. For instance, on the challenging ImageNet V2 dataset, an ImageNet pre-trained VIT base achieves 88.55% accuracy, significantly outperforming previous convolutional baselines.
So the transformer's ability to model long-range dependencies, combined with enough data to learn local features, makes it a powerhouse for vision tasks now too.
Precisely. It showcases how the core idea of attention, without explicit assumptions about local structure, can generalize across modalities when given enough data and proper input tokenization. It's truly a universal architecture.
From words to image patches, it seems attention really is all you need, provided you feed it right and train it well.